Welcome again to the NPTEL course on storage systems. In the last class, we were saying that to contain the complexity of writing a file system, typically some abstractions are used. Some of them are related to manipulating buffers, some of them are related to managing inodes, and there are similar ones for managing other data structures. The ones I have listed here are the ones that have come traditionally in Unix file systems. For example, the ones I am listing here are what are those found in Unix SV3, okay, that is System 5 release version 3, and you will find it documented quite well in the book by Maurice Bach, The Design of the Operating System. Okay, I am taking the examples from there. Okay, so this just gives you some idea that there is some inherent complexity in designing a reliable file system. Therefore, the only way to get it right is to use certain interfaces that have proved to be useful as a way to, let us say, structure the writing of the system call. And you will notice that in each of these cases, there is a specific locking aspect also built into it. For example, when I get a locked inode, because this seems to be a common idiom. So, the common idioms have been factored into certain types of internal interfaces. Of course, these internal interfaces are not, let us say, cast in stone, they will keep varying as designs evolve, and what I am giving you right now is only what is found in Unix derived file systems, and if you go to completely non-Unix or even very recent file systems, they may not have this kind of interfaces. There are internal interfaces, nothing is guaranteed about its availability as time progresses. Okay. But these are good to think about, because you will get some idea about what is involved. Let us just take a simple example. These kind of interfaces were designed at the time when file systems were small. For example, 40 megabyte file systems, things like that. So, the chances of any errors happening were small. Okay. And so, you will notice that there is an implicit assumption in these interfaces that the inodes are not replicated, neither is data replicated. Whereas, if we look at advanced file systems, the current generation file systems, which try to handle not just terabyte, even petabyte things, if you do not replicate inode, the chances of your surviving, keeping a file system intact is almost negligible. Okay. So, these things assume that there is only a single inode, there is no copy of it, or there is no interface by which you can talk about a single copy of an inode. Okay. None of these things is there. Okay. So, if you really try to think about it, the internal interfaces will keep changing because of different needs, different perspectives as time progresses. Okay. Again, as I mentioned, this is an older one, this is as of mid 80s or early 90s, and but you will find all Unix derived file systems typically have something similar to this. Let us just quickly look at one particular operation to make certain things a bit more concrete, to see how it looks like. In POSIX kind of file systems, you have a notion of a link, and basically what is attempted is that you want to, there is a source file and you want to create a name in a particular directory which has the same inode as that of the source. This is the source inode, and this can be the target file name / target directory. If it is a target directory, then you want to create the same name as this source file name and has the same inode as the source one. That means there is a single object, single file with two references. Okay. It depends on what the target is. Target could be a directory or it could be a file name. Okay. Depending on it, the appropriate discrimination is made. So, let us see how this works out. So, what is to be done here? First of all, I just want to illustrate how some of the internal interfaces are used. Okay. Again, I should mention that this is a mid 80s design. So, concurrency levels are small. That means the only concurrency that people are talking about here are because of other interrupt generating devices, for example. This is the only thing that are running concurrently with this kernel code. Okay, nothing else is running concurrently. Okay, there's only one active thing in the kernel. Any other concurrent thing is mostly interrupt driven interrupt routines. That's all. Okay, so that's why the code looks a bit simple. But if you think about more recent file systems with attempts to really concurrentize lots of operations, it will be not this simple. It will be much more complicated. Okay. So let us see what is here. First of all, as I mentioned, source is a file name which has to be, let us say, you need to create another file name which has the same inode as that of the source. Okay. So what is the first step I do? I do name I source. What does name I do? It basically does parsing of the file name, and then finally, after doing all that parsing, after so many levels of parsing, it figures out the corresponding inode for it. Okay. So this is an example of an internal interface that is being used, name I. So basically, it gets inode for source. Okay. Now, one thing about operating systems and of course storage systems is that you have to do extensive error checking. So there is usual error checking going on all over. Every single line or other line will be error checking. Okay. So as usual, if it checks whether does it have too many links on file, it may be that why are you checking for this kind of things? It may be there is a bug in the system somewhere. Somebody has written a loop that is just linking out of control. Okay. You just want to catch all those kinds of things. Usually, it helps to catch those kind of errors as quickly as possible. Okay. Normally, what happens is that the number of links is a field. Usually, it's about, let us say, 8 bits or 6 bits or whatever. So it can overflow also. So the thing is to see if there is a way to catch it. Okay. That's why they are trying to do some of these things. Okay. Or if somebody is trying to link directories without super user privileges, it's possible for root to do linking of directories. Okay. Now, super user can do it, not users. So in case this happens to be that there are directories involved, for example, source also is a directory, then this should be disallowed. So that's what it basically returns an error. But before that, you already got the inode, and when you notice that when you get the inode, you got it locked. Okay, that's what the semantics of name is. Okay, so you have to basically put it back. You release the inode. Okay, you got it locked here, you have to release it. So because you are going to return an error, you better clean up before you go. That's what you do. You are cleaning up and then going back. Okay. Now the next thing is, since you got it in memory, you can certainly, there is a disk inode, there is a memory inode. So in the memory inode, increment the link count. Now this particular thing is basically saying that even before I have done anything, I can increment a link. And this, what is philosophy being followed here? Better that I point to, so there are two possibilities. I have to avoid the following. Okay, I should not point under any circumstance to garbage or to a null. I should not have a null pointer reference. That's something I have to avoid. The other possibility is that I don't mind some garbage being created. Okay, okay. So idea here is I don't mind garbage being created, but I want to avoid the situation where I point to illegal structures. That's basically what I want to avoid. Okay. So what am I doing out here? What is the policy being adopted by this mid 1980s thing? It says increment link count on inode. So the question for us is, why is it safe to do it? Is it safe, or is it could it get into problem? That's something you have to think about. Okay. Now, if in case you have increment inode and then you update the disk inode, right? That means even before I have done anything, I already updated it. Suppose there is a crash here. Okay. Now the question is it possible for me to recover from it? It turns out that FSCK can recover from this because it follows all the pointers and it finds that it is actually pointing to only one thing, what is on that. Okay. And therefore, it can say that it can reset the link count to exactly 1. So as long as we assume that there is an FSCK which can track every single pointer on disk and then count the number of references, then this is a safe thing to do. Okay. So increments the link count on inode, update disk inode and unlock. Okay. Now why does it do unlock here? Because I am going to do now another name I. which can take a long time. Okay, because again this is again a path traversal, because the target is here, I have to do a path traversal. Since it can take a long time, I want to let other people who could be using, who want to just look at it quickly. For example, somebody could be doing a stat call. Okay. So, luckily the thing is already cached in memory, that guy can really look at the thing quickly and walk out. Okay. I want to allow those kind of things to happen. That is why I drop the lock, and then when I need it, I will take it again. Again, this is an example by which they are very conscious of the fact that we are dealing with the slow devices, okay, extremely slow devices. We are talking about milliseconds, tens of milliseconds. So, in which a lot of things can happen, therefore, they unlock it. Now, you go and try to get the inode of the parent inode where this particular new link has to be present. You could have specified a directory here. Okay. That means I have to get the inode corresponding to the directory, or I could have specified a target file, in which case I have to look at the target file and then remove the end part, take the directory part and then look it up. Okay. That is what the name_i is going to do. Okay. It is going to come, now it is going to figure out what is the directory in which this new target file is going to come in. Okay. Again, it uses name_i, again as I mentioned to you, it can be a long operation. It is a path traversal, it can have multiple components /a/b/c, whatever it is. Okay. So, in principle, it can take 150 milliseconds if you are stuck and it has to be picked up from there. Okay. It is a long operation, that is why this unlock is there. Okay. Now, standard things, if new file exists or source target on different file systems, something is not okay, we can drop it. So, if the new file already exists on the directory where it has to put, you can't do that. Source target on different file systems. Now, you are doing what is called a hard link. Hard link demands that, because you are sharing the inode now, you are not creating any new data, they are just creating a new name in the file system namespace and then pointing to the same object. So, it has got only one representation. Okay. So, it cannot be on a different file system, because different file system could be having a different, altogether different type of file system. For example, it could be ext2 on one and ext3 or let us say ZFS on something else. Now, these two guys cannot share the same inode, because they are two different animals. Okay. That is why it checks whether source and target are on different file systems. Okay. And then if that is the case, then it is not possible, but I have already updated the disk inode, I need to undo it. Okay. Now, of course, there are some problems here also. It may be that at this point I crash. Okay. Again, we are hoping that FSCK can fix it, right. So, at every point it can crash, at every point you need somebody who can tell you whether they can recover cleanly and come out. Okay. So, luckily here also there is no problem, just like we could recover from here, we could also can recover from there, nothing else has happened. All you have done is we just picked up we just did a path name, a traversal, and then we figured out what the inode is, nothing else has happened. Okay. Now, after this, you create new directory entry in page directory in the parent directory corresponding to the target file, or and then basically in the new directory you have to take the new name and the corresponding inode. So, basically directory is basically nothing more than a map between name of file and its inode, that is all it gets. Okay. So, that is what you have to introduce these two components, the new file name and the inode that you picked up here of the source. Okay. Once this is done, I put the parent directory, because I want to release it. What does release mean? Because notice that when I got all these things name_i, it is always locked. So, I am again releasing the lock, and that way it is staying in memory. So, if somebody else wants it, they can again get it in memory, they do not have to go to disk. Same thing with the source also, the source file, I also do an I put, I release it. Okay. Now, this roughly the outline of a link command, and it's quite simple the way it looks, but in practice with concurrency, with multi-threaded kernels, this is not going to be easy. It's not going to be that simple. Okay. What will happen often is that you might find that as you are doing things, things can change. For example, as I mentioned here, you unlock the inode here, right. In a concurrent multi-threaded kernel, it may be that by the time you get to doing this, somebody has deleted this particular source inode itself. It is possible. Okay. So, you have to be careful. Okay. You have to keep checking things again, because notice that nobody has taken the lock on the directory where source is present. I think nothing is here, as far as I know there is no place here which takes the lock on that. That means that in principle some other party could have come and deleted this thing. So, you have to, as you go along, you have to keep telling yourself, if there is concurrence in the system, could somebody have come and taken it away from me? I thought it was going to be there, but as I am working and doing something, I am doing that path traversal for the target, somebody else could have come and run away with my inode I thought was present to me. So, again I have to check it. Okay. So, there is an extensive amount of checking that goes on. Okay. And so, things are not, of course, the easiest thing is to just take a lock on this itself. If you take a lock on it, it is possible that you are extremely slow, because basically you are saying I lock everything and then only do something. So, if you are basically pessimistic, totally pessimistic, you are assuming that some all kinds of bad things can happen. So, it is something like going on a road with a battle tank. Okay. You are going to be slow. Okay. Whereas, here what the typical, because finally a file system has to be quick and fast, otherwise it is going to be extremely slow. Okay. So, the strategy is to say that I will be optimistic, I will release the locks as and when necessary. Okay. There are some situations where the kind of stuff I am looking for, somebody unfortunately is contending for at the same time. As long as I assume that that is infrequent, then in those cases only I suffer this rechecking cost. Okay. I check the cost and it is available immediately, I do not have to worry about it. I do small amounts of, I incur the cost of checking, but typically it is always successful. Typically nobody is run away with it. So, it is not a cost, serious cost. Okay. So, concurrency really changes the whole game, it is non trivial, and that is the reason why even today you will find established file systems, you find new bugs. It is not because it is just inherently the fact that there is a lot of concurrence in the system and there are lots of interleaving things that can happen, and there are no models of what is correctness in a file system or for that matter in an operating system. Okay. Essentially it is by long practice certain things are considered reasonable. I will come to that, I will show what the semantics of file systems are. Okay. And because of that, it turns out that it is not easy to specify what exactly is quote a correct file system operation, because it will become clear as we talk about it. Okay. So, again I will give you again a slightly high level idea about a write. This is again an extremely simplified version, and we will just go through what are the steps. Okay. Typically write tends to be some of the most complex operations in a file system. Okay. First, one thing I should already mention is that, which I have already mentioned, is that when you do a write, you can be coming from an application which is using something like fwrite. Okay. Fwrite is a libc call, and libc somebody has to look at fwrite and convert it into a system call. Once system call comes in, you now have entered the kernel. Once you entered the kernel, you first go through what is called the it is called BFS. What does it stand for? File system independent operations. Okay. So, you have to go through the file system independent operations, and there are certain things which are done in the file system independent operations. What are those? Typically it is security. What is involved in the security? There are multiple models in file systems. In older systems or simpler systems, you have what is called discretionary access control mechanisms. In the more secure type of file systems, they try to give you what is called mandatory access control systems. What is the difference between these two things? In discretionary access control mechanisms, what happens is that if somebody is given a permission, he in turn or she in turn can give that object to anybody else. Okay. You have got an object in your hands, you can give it to anybody as long as you want it. Okay. So, whereas in mandatory access control, even if you have access to the object, you cannot give access to it to anybody else. It has to be checked, it will again be checked by some secure part of the system to see if it can be given to anybody else. Okay. So, when you look at the write call, it will check whether you have which of those credentials do you have. Do you have DAC credentials or MAC credentials, and only if you have the appropriate ones you are allowed. Okay. Other thing is, writes can have what are called range locks. For example, there are some locks available at user level, there are some locks available at the kernel level. What are the kinds of locks available at user level? There is something called FNCTL. Okay. FNCTL basically says, it says file control. So, you can take a lock on a file starting from a particular offset to some other offset. Okay. So, this is actually visible to the user or visible at the programming level. Okay. So, this has to be definitely be supported. Okay. So, this is one lock that is visible from the outside itself. But the other locks also, which have to be kept for internal consistency of the file by the file system. Okay. We will come to that a bit more in detail. Okay. So, this is another lock that has to be handled. Okay. It actually turns out that the number of locks can be dramatically large. If you look at a production quality file system, you will find that in addition to the user visible lock, you might have as many as 30 locks for a single file inside the kernel. Basically, because you might have various locks protecting various parts of the files of the file, okay, or the metadata. Okay. So, the basic reason being that you want to allow as much concurrency as possible. So, invariably it turns out that if you have a coarse lock, it turns out it hinders some other operation which could have proceeded in case there were finer grained locks and you did not actually contend for that part of it. Okay. So, as I mentioned earlier, file system operations can be slow compared to memory operations. Therefore, anybody hindering it because of this can be delayed by as much as disk speeds. So, it can result in arbitrarily slow performance if you are in a loop or whatever, and therefore, sophisticated file systems try to give much more granular locks, but that itself creates amazing complications, because once you have so many locks, then you have deadlock possibilities coming left and right. Okay. The numbers of possibilities just explode. So, you have to really have a extremely tight coding standards to get anything working. Okay. And it is not just the locks that is of the file system, it will also be the locks of the VM subsystem, virtual memory subsystem. And as we discussed before, there is a strong interaction between the file system and the virtual memory subsystem. And the virtual memory subsystem also takes certain locks. For example, address space locks. If you are doing a mmap, it will take address space locks, okay, and other kinds of locks corresponding to the VM part of it. So, when you are doing some operation, there has to be some ordering of locks across all these also. So, designers of these kind of file systems carefully think about ordering of these locks and then only proceed with it. it turns out to be non-trivial. These things are better done by experts and let us say people with a lot of experience. Of course, one way to avoid all these problems is to say that a file system does not belong in the kernel, it should be outside of it. Okay? Like in a microkernel operating systems, the file system like Minix 3, it puts the file system outside. So now the interaction between the file system locking and the VM locking can be eliminated a bit, but it turns out that it has other problems. Okay? Because concurrency is concurrency. If you can exile the file system outside the kernel, but if you are planning to do concurrency, there will be some locks at the file system level, at the user level. Even those things also, if you want to do it efficiently, you need to have multiple locks there, and they will also interact with other locks, and the same kind of problems will occur. Just like POSIX pthreads programming is complex. You can get into deadlocks at the pthreads level. So for the same reason, you can also do the same problems in the file system level, even if you take it outside the kernel. Okay? So you cannot really wish away the problem of concurrency. Wherever you are, you have to face it. Okay? It's just that it might make it slightly easier if you are wanting to debug it, because if you are outside the kernel, debugging is that much simpler compared to debugging inside the kernel. We have lot more infrastructure outside the kernel compared to inside. Okay. So again, as we mentioned before, if you are wanting to report access of a file at any time that file is accessed, you need to have some triggers. Again, there is some wrapper routines out here. Okay. Now, one thing that you have to remember is that you need to figure out how to continue after reporting this event. So in general, you need what is called continuations. You have walked into the kernel and then you detected the situation that you needed to report it to somebody, but after reporting you have to proceed. That means that there is some continuation that has to be kept around, so that you report, typically you do an upcall, you go outside the kernel, it does whatever it does, and then you have to come back and start exactly where you left. Okay. That means you need to save the state of the kernel stack, and then switch the stack to the stack of the called procedure which is outside the system. Okay. So you need to manage this business of stack swapping, etc. carefully. Okay. Again, if you are talking about sophisticated file systems, these are complicated systems. There are many reasons why these file systems have to be frozen. That means that you want to freeze all the activity within it, so that you can do some surgery on it somewhere. Oftentimes, just like you anesthetize a patient, you have to anesthetize a file system, because there are too many components in it. You can't do some major surgery without ensuring there is no. You should make sure there is no activity while you are doing the surgery. Okay? Otherwise, some things can go really bad. So you might have to freeze the file system. That means that you have to, before freezing, you have to figure out what all the activities that are there, and you have to make sure that each of these activities is going to be terminated in a clean manner, made to somehow come out of the file system if possible, or if it cannot be made to come out of the file system, you have to somehow get it to a consistent state, some easily checkpointable state. Okay. Now this might look this simple, but actually it turns out to be fairly complicated. Reason being, as mentioned before, a file system interacts with the VM subsystem and other subsystems, and they can do mutually recursive calls. That means that you could have come in through the file system and walked into the VM subsystem, and the VM subsystem could be doing swapping operations which is running on another file system or on the same file system. That means you have made a recursive entry into the file system. Okay. Now you have to keep track of how many times where have I come in from, and where do I have to go out. In some sense, again, as I mentioned to you, you need to keep track of the continuations. This turns out to be non-trivial. Okay. This is something also we have to be careful, and you need to provide some infrastructure by which you know how you came in and how you can safely come out. Okay. So basically you can freeze a file system, you can thaw it also. Okay. Thaw it means you have passivated the file system, and then once the surgery is done, you want to get it going again. When you get it going again, you have to see what state you left it in and slowly bring back it in the right way. Okay. And unfortunately, the details are complex. So, but given in a file system, there is some, with some careful engineering you can get it done, okay, but it is non-trivial. Okay. Okay. So, these are some of the things that you have to also provide. Basically, I am saying is that when you enter the file system for a write, you have to record the information somewhere, okay, and what level you came in. Did you come in the first time, or you coming through some other, are you making a recursive entry, etc. Okay, you have to record all this information somewhere, okay, and you have to do it efficiently. You can't remember all kinds of things, okay, otherwise the structure becomes too complicated. Okay. So you note some information about how you came in, okay. And the next thing is you have to do a BMap. As I mentioned to you, what is a BMap? It basically, given a file and offset, it tells you what is the block corresponding to that particular starting address of the starting block address. Okay, you have to do BMap. Again, this one can be non-trivial, because to do a BMap, you may have to go and pick up the direct blocks are already available, but indirect blocks have to be picked up. That means that as I am doing BMap, I have to go to disk and pick up direct and indirect blocks. Okay. Now, that means that your system is sort of your call is waiting while a disk operation is going on. Okay. So, what it means also is that while that is going on, it is possible that concurrent activities might invalidate some information. Again, you have to do some rechecking again. Okay. So, there are issues of even in something like BMap, in a concurrent multi-layer kernel, there could be lots of complications here. Okay. Some of these things, the actual code is really amazingly complex. Okay. The even worst part of it is that there are no specifications. You have to do what is required to get most of the application code running correctly. Okay. As I mentioned to you earlier, there are a lot of scripts out there. If you get some of the script, if you get your file system semantics slightly different than what people are expecting, they will say that the file system is buggy. Okay. But there is no specification, there is no way to, you can't prove that somebody is buggy because there is no specification, but they will tell you you are buggy. Okay. You have to go and fix it. Okay. And things typically are connected with all this flushing, all those kind of things. Yes, you can leave certain things in memory, you do not flush it, and somebody is coming to some other interface, and since they are not coming to the file system interface, they can see something else. For example, in many file systems, you can come through, you can access the same structures through the file system interfaces, or you can come through a device interface, because in Unix, a device also is a file, okay, and you can export it, a file also as a device, okay. And if you do all this called loop back, there is something called loop devices. You can take a file and think of it as a device, and then you can put a file system on top of it. That is as a single file, 1 GB file, and then you can tell the file system that I am going to think of it as a device, and I am on top of it I am going to put another file system in it. That full 1 GB will be a single, it is going to multiple internal structure is going to be there. So, because of these kinds of looping and recursive structures, it is non-trivial to get a semantics right. Okay, I will also go through it a bit. Okay. So, other thing that what it has to do is to think of appends and override, the difference between append and override. Appends are slightly easier because all you have to do is to go to the end and to extend it, but then you have to worry about concurrent appends. How do you ensure that only one of them appends? You have to make sure that append is complete before the second append comes in. Okay. That means that you need to take specific locks. Okay. And the way sometimes people do it is to have lock on certain length sizes, for example. And you can also have overrides, and overrides can have holes in it. That means that you can do allocations here also. So, BMap can do reads of disk blocks, overwrite, what can happen is that you have a file and somebody has, without writing anything, it has seeked to the person has seeked further along. So Unix has the semantics that if you seek, you can have holes in it, that means the blocks are not allocated. Now you can write to that hole, that means there is no block there, that means you have to allocate a block. So in overwrite it can turn out that you might have to allocate blocks. Okay. So that means that as a part of write, you could be talking to various block allocation routines, okay, and you will also be updating the number of freely available blocks and other kinds of things. Okay. Okay. So sometimes you also have to worry about some specific things. It turns out NFS write is a major issue because they are synchronous. Okay. So for a long time NFS was synchronous write, and synchronous writes, as everybody knows, is slow. So the idea is to see if the something can be done to make it fast. Okay. So there are a lot of heuristics to discover if a write is an NFS write. That is, you have a local file system, and through NFS client is asking something to be written, it is coming to the NFS server, and finally it is going to the local file system. The local file system sees it as a write. It does not know it is coming from NFS, that is coming from NFS client, because it is being redirected to the NFS server. So it has some heuristics to figure out that it is probably coming from NFS thing, because usually 8K is usually considered a signal that there is probably NFS write, because NFS writes are typically 8K, 8 kilobytes. So it will actually guess that something is NFS write, and probably it can do some logging. Okay. It basically, instead of writing it, because the problem with writing it synchronously is that you are going to take the diskette. So what you want to do is to see if you can log it. Anyway, you are going to do a lot of writes to disk as a part of other operations, and you are creating a log, and you log the NFS write itself onto the log, and it will go as part of every other so many other writes, like so many other file system activities that are going on concurrently. So you might actually amortize the cost of flushing to disk. Okay. So there is some support for these kind of things also. Okay. And other issue is, in advanced file systems, typically writes are written by kernel maps. Okay. What you do is, you take the file that has to be written, and you map it to a kernel address space, and then you copy it from the user buffer into the kernel memory. Okay. This way what they allow you is that there is a single copy of the written stuff, it is not there in two places. For example, if you do it in a older types of file systems, you will find that you will be having it one copy in buffer cache and one copy in the VM subsystem. So by doing this kernel maps, you will have only a single copy, and that turns out to be quite efficient. Okay. So again, all this segmap etc. also, that means that you are now actually using virtual memory subsystem calls to implement this. Okay. So this is another example how the file system is very tightly connected with the virtual memory subsystem, and as part of writing it, you might actually suffer a page fault, and now again you will enter the VM subsystem, because that has to be handled by the kernel. When you try to write from the user buffer to the kernel mapped region, you might suffer a fault, and then the kernel will notice that this has been because of a segmap write, and then it knows that it has to bring the corresponding blocks, okay, or corresponding information that is present in the disk. It has to bring it back, and so some of those things also have to be done. Okay. And usually what happens is that this particular disk actually could is present as part of the file system, because you are writing a file system code. that means that only file system can parse it. So, the kernel might not understand how to pick up that particular block. It only knows that it is a file followed by a particular offset. That again it means that it has to talk to the file system, and the way it is done is by calling something called a get page routine. Okay. You are basically saying, the kernel basically says there is a fault here and you are the only person who knows how to read it, because all I know is a file and offset, I don't know anything beyond it. And this file and offset information is not file system specific, it is file system independent. So, that is all it knows. So, again it has to tell the file system that please go and bring your file with this offset. So, that means that again it has to, the file system is again re-entered for the get page. Okay. So, we enter the file system, and so basically we are doing a write. As part of the write, we have gone into the VM subsystem, and the VM subsystem there is a fault while you are writing it from the user address, user buffer to the corresponding place in the file system that you are supposed to write, because it is not already present in memory. You fault, because you fault, you have, all you know is that you have to pick up that buffer from the disk, and only the file system knows how to parse that information. So, again that means that the VM subsystem itself now calls the warp get page. Okay. And so, get page is done, the corresponding block is picked up and brought to memory by the file system code independently. It is the second operation now. Okay. Once that is done, then the VM subsystem comes into picture, then it now finally gives that page, it is available in memory. Now, the write actually can start, the actual write. Okay. And this can happen every block, every page it can happen, these things. Okay. So, it turns out, again I simplified it very much, it turns out there are so many other concurrent operations going on at the same time, because the pages can be deallocated, it can be, for example, there could be another file system call which is doing what is called truncate. What does truncate do? It basically says, I want to chop off this portion of the file from here to here. That is, I have a file which is, let us say 8 megabytes, I can say truncate to 0 bytes. Okay. So, somebody is running this particular system call in parallel with my get page routine. Okay. What is the semantics of this? You have to decide. Okay. Normally, the understanding is that if somebody is doing a get page and there is a truncate going on, okay, then you have to think about interleavings. Okay. So, either way, right, whether you have a get page or you can either do the get page first followed by truncate, or a truncate followed by get page. Okay. Normally, the semantics is that anyway the truncate is supposed to, if it is done, right, irrespective of which order you do it, it should not result in any pages to be given. That means you have to stop all get pages, right. So, you need to prevent get page to go through when a truncate is going on at the same time. Okay. That means there is a specific lock for this purpose. Again, we will talk about it soon. Okay. So, so there are a lot of issues of this kind that the file system designer has to worry about. So, it is highly specialized kind of work with no specifications that are available across consumers and file system designers / implementers, okay, unfortunately. Okay. So, it creates lots of complications. Okay. In addition to all these things, you have to manage the log space. You might be running out of memory, because first of all when you do a logging, you first do it in memory, then only you push it out to disk. It is possible that you run out of memory. When you run out of memory, what can happen? You want to see if there are any buffers that can be flushed to disk, right, or you want to see if any delayed writes are there which is storing, which is holding on certain files which are in memory, which could be profitably sent out to disk. That means that as a part of this whole write itself, I might be doing some disk flushes, which also can take some space, time. While that is going on, I cannot really proceed, I just have to stop here, right. So, and what is interesting is that while I am doing the flushing, it may turn out that they might suffer some errors, okay, because nobody guarantees that anytime I do a write, it is going to go through correctly. The disk might fail, anything can happen, okay. That means that again there has to be some infrastructure in the kernel by which, while I am trying to do some operations of this kind, if there is a problem, I come out of it clean again, okay. That means that there has to be some kind of minimal information that I have to keep here, okay. In some sense, it has to be some kind of checkpointable information. So at every point you have to keep doing this, okay. And so you have to manage the log space, etc. You have to do the logging, you have to do the flushing, all those things have to be done. First of all, manage the space, ensure that everything is okay, then you start doing this logging and flushing, okay. And other thing that we have to worry about is manage visibility of current write to other system calls. As I mentioned to you earlier, if you are writing to, you are appending to a file, the question is what can other people see as you are doing it? Can they see it at all, or can they, you have to complete the job before anybody can see it, okay. Now different file systems, again this is one example where the specifications are not available, okay. Nobody tells you what the specifications are, okay. So different file systems, aggressive file systems do one way, the simple file systems do a simple way. For example, if you are a simple file system, you basically say until I finish my append, I won't let anybody see. That means that the other parties who are concurrently looking at it, they will see the file as a static object, okay. They will just see it as not being extended. Whereas if you are an aggressive file system, you want to ensure that as you are writing, as you are appending it, if it has crossed a certain threshold of a sector or of a block or whatever, I want to keep on exposing it to other people that the file has been extended. Even a mapped file can see these extensions, even though it looks a bit hairy, but it can be done. So, okay. So the question is how much visibility you are providing into this operation, which is let us say, do you want to view it as a atomic operation, or you want to view it as a somewhat let us say long operation with multiple small things being atomic, okay. So again, depending on what you do, certain applications will work, certain applications will fail, okay. For example, if there is a mail reader and then somebody is extending the file, and then while if the write is going on, let us say, right, the write can be long, because for example, it may be that somebody has taken a huge file has come from somewhere, okay, and it is being appended, it could be a megabyte or so. During the, while that is being written, you will probably get some information that no files have been transferred at all, okay, which can actually possibly cause wrong information to be given while you are updating the file, okay. So there are differences in file systems how they handle this. In addition to all these things, we have to allocate virtual memory areas and buffers, those also have to be handled, okay. Again, once you are done with the write, you have to drop the locks, you have to the freeze and thaw information, you have to update it, the trigger information, you have to again let us say complete whatever has to be done at the end of this triggering operation, etc., etc. All these things also have to be concluded at the end. So generally, what are the kinds of issues in single thread kernels? As we mentioned before, interleaved execution of things like get block with interrupt blunder, or with the get block with B release, okay. Okay, there are some interleaved executions which can create problems, you have to work out the details, okay. That means that every single interface, how it interacts with every other interface, every interface, internal interface, how it interacts with interrupts, it has to be worked out, okay. It is a painstaking work, it has to be done, okay. So generally, if you want to avoid this thinking about this interrupt handler, you have to block it, interrupts, okay. So in multi-thread kernels, you have to also worry about other concurrent system calls, okay. In addition to these things, you have to worry about other concurrent system calls. You have to important thing about this is that you have to avoid deadlocks at all costs. If your file system gets deadlocked, you are dead. Okay. Critical piece of the infrastructure, kernel infrastructure is dead. Okay. It's not possible. That means that you have to do what is called deadlock avoidance, and in case there is actually a deadlock avoidance as much as possible. If there is once in a while, if you really get deadlocked, you may want to really provide some ways to break the deadlocks. Okay. Usually deadlock avoidance is what everybody attempts as much as possible. Okay. So, for example, you have to use lock ordering where possible. For example, in a rename, what is a rename? You basically saying that a certain part of the file system tree is going to be given a different name at a different place. You are basically grafting one part of the file system space to some other place. Okay. So, you basically have to log the source and target directory entries. Now, what can happen is that somebody can be doing a rename in the opposite direction. Nothing prevents it from happening. Okay. That is, I am doing rename from A to B, somebody could bring from B to A. Okay. You have to assume the worst case. Okay. So, then basically what you have to do is you have to find a way of getting the some object at least, for example, V node or I node or Z node or whatever, right. Okay. In the case of ZFS, it is called Z node. You basically find log the directory of the smallest object ID first. Okay. These are numbers, it does not matter what it is, just take the smallest ID. Okay. You take the lock on it first, followed by the one with higher number. If it so happens that your rename actually has the same directories, because I can always rename two files which are in the same directory. I can rename a file in one directory to be some other name in the same directory. Okay. That means that the source and target names will be the same, there is a tie. Therefore, then you have to figure out the name of the thing, figure out which one is going to be earlier. So, you have to have some kind of mechanisms. Okay. If it is not possible to order, then you always take locks opportunistically, and then the minute it looks as if there is a deadlock kind of situation, you drop locks appropriately to come out of it. Okay. You have to be doing it all the time. And as I told you, one thing about concurrent operations is that while you are taking a lock, if you are waiting, the world might have changed. That means that the state of your model of the system while you are waiting for a lock will not be the same after you got a lock. Again, you have to revalidate all the locks again to see if you got it. If you can't get it again, you loop it again. You have to do all those things. Okay. And generally, you have to get all the standard way to avoid deadlocks is to get everything you need first in your hands, then only do the operation. Okay. If you find that you do not get all the resources, you just you give back all the resources and retry it again. That is a standard method. Basically, the thing is there is something called, you want to avoid this wait and hold condition. Okay. Hold and wait condition. Okay. If you hold and wait, then other person also can do hold and wait, and you can get locked. So, the ideal thing is never to do this hold and wait. That means that you basically have to get everything you want. If you can't get it, you drop all of it again, retry again. Okay. So, there's these kind of issues, and generally locking is the biggest headache in concurrent file systems in highly multi-threaded kernels. Okay. This is the most difficult problem that you have to handle, given the high numbers of locks and the lack of complete specifications and what supposedly a file system is supposed to do, what a system call is supposed to do. It is based on experience. Okay, how you do these things. Okay. As I mentioned earlier, to freeze and thaw file systems, you need some infrastructure to count how you came in, how you are going out. Okay, you need to keep that infrastructure. Okay. With errors and triggers, anytime there is error in the kernel or in the file system code, you may have to find a way to coming back. You have to get back in some reasonable condition. So, you basically have to store continuation. Every time you go to disk, there can be a failure, anytime you go. Okay. So, this is something you have to worry about. Okay. So, I think in the next class, I will talk a bit about file system semantics and see how that is handled, and then I will go into one file system. I decided to look into what is called the ZFS, which Sun originally designed, and now it is with Oracle. Okay. So, I will go through ZFS. The source code of ZFS is available. So, it is an example of an advanced modern file system which tries to do a lot of interesting things. So, it is good to look at it if you really want to take a look at it, because the source code is available and it is in the context of a fairly sophisticated operating system like Solaris. It will be, if somebody wants to really look into details, they can take a look at it. Okay. Thank you.